So I want to use some sum and difference
Sasquatch is in the ceiling.
identities, which I just spelled wrong because Henry's making Sasquatch noises. To solve equations. And this caused a lot of issues last year because we never specifically looked at these examples, but I feel like if we just look at one is probably going to be enough to get the point across. Is that if you have some sort of an equation where you have thetas and functions of theta and functions of 2 theta kind of mixed together, you're going to want to kind of parse them out and separate them and kind of not get them jumbled together. So it's much easier if you just see what I mean here. If we had something like sine of 2x equals the sine of x. So now these functions have different inputs. One of them is the right-hand side. We are just inputting x into the sine function, and then we could evaluate. But on the left-hand side, we're inputting x. That gets doubled before I evaluate the sine of that particular value. So as this is set up now, I could only kind of guess and check. I can't really factor this because if I subtract sine x from both sides, they're not really like terms that I can factor out of because they have different inputs within the sine function. So the only thing that I have to do is that I can use an identity to replace the sine of 2x. So I can do this one of 2 ways. I can use the double angle identity for the sine of 2x or the sine of 2 theta, which is on my formula sheet. Or I could just rewrite the sine of 2x as the sine of x plus x, and then use the sine sum identity to replace the sine of x plus x. Both will get me exactly the same answer. So since I just made a video using the sine sum formula, I'll use the double angle, so I know that the sine of 2x is 2 sine of x cosine of x. Now once I get to here, now this looks like an equation that I can solve. So I'm actually going to solve this in a way that I see a lot of people doing, and I'm going to indicate sort of a mistake that I see along the way. So typically when we've been getting to these equations, people have been like, well, I'm going to divide sine of x off both sides. That's totally a fine step. And we wind up with 2 cosine of x equals 1. So now that means that cosine of x will be a half. And now I need to sort of think of reference triangles and the unit circle and the coordinate plane to find all of the radian values where the cosine of x is a half. So if I drew out my triangles here, I'd be in quadrants 1 and 4, thinking about all students take calculus. Cosine is positive in quadrants 1 and 4. And I believe that the triangle is going to be a 30, 60, 90 triangle with a reference angle of 60 degrees, which is pi over 3 radians. So my answers here will be pi over 3 and 5 pi over 3. I'm sorry. No, 5 pi over 3, yes. And I'm solving for all possible solutions here. I didn't specify over any given intervals, so I'm going to add plus 2 pi n to each of those and specify that n is an integer by either using math notation or just literally writing out that n is an integer. Great, so those are definitely some solutions to this equation, but the problem here is that I divided off sine of x on both sides of the equation, so I actually kind of lost some solutions, because if I look back at the equation 2 sine of x cosine of x equals sine of x, if sine of x was 0, so if this was a 0, and if that was a 0, 2 times 0 times cosine of x is 0, and that would equal 0. So if sine of x is 0, that's actually a solution to the equation that I lost by dividing both sides by sine of x. So a lot of people I see doing proper math, solving these equations, but are often not going back to think about if they lost any of the equations by, say, dividing both sides. by a particular quantity. So now I have to go back and also solve for when sine of x is 0, but that's a fairly easy equation to solve. Sine is going to be 0 at 0 radians and at pi radians. So x is going to be 0 and pi, or I could just say 0 plus pi n, and that would cover all of my solutions. And I've already specified that n's an integer, so there's all my solutions. So again, the key there was in the fact that I needed to use an identity in the original equation. Let me just write the original equation one more time. The key here is that I needed to use an identity to substitute some other quantity for the sine of 2x, or I wouldn't kind of be able to solve this equation unless I wanted to kind of guess and check all of the possible values. So again, using the identities for substitutions, you're going to do that when you're proving identities, but you also may need to do that when you solve equations on the test.